Hello, discrete math fans. Let's talk about modular arithmetic. Now we're going to start playing real fast and loose with the idea of divisibility. We're going to be a little less formal. Now there's a theorem in the book that gives a whole lot of equivalent forms of divisibility. What we'd like to do is state the theorem without proof. The proof is not particularly illuminating. So the theorem goes like this. If you have integers a, b, and n, with n bigger than 1, then these 5 statements are all equivalent. What it means for those statements to be equivalent is that if any one of them is true, then they're all true. If any one of them is false, then they're all false. So the first statement is n divides a minus b, or we could write a is congruent to b mod n, or we could write a is equal to b plus k times n for some k in the integers. Or we could say that a and b have the same non-negative remainder when we divide by n. And finally, we could just say a mod n is equal to b mod n. Now if we go back to the quotient remainder theorem, if we take an integer a and divide by a positive integer n, then we get a quotient and a remainder, a unique quotient and remainder. This quotient and remainder has the property that a is equal to qn plus r, and r is between 0 and n. Of course, we can't have r equaling n. Now we should note that there are exactly n integers that satisfy this inequality. They are the numbers 0 through n minus 1. So there are exactly n possible remainders that you can get when you divide by n. These remainders are called the least non-negative residues modulo n, or simply the residues mod n. And speaking of being more informal, notice that sometimes I'll just say mod instead of modulo. That's perfectly acceptable. Let's give a definition to tie all this together. If we have integers a and n, where n is bigger than 1, then the residue of a modulo n is a mod n. It's the non-negative remainder that we get when a is divided by n. And the numbers 0, 1, 2, up to n minus 1 are called a complete set of residues modulo n. Then we can talk about reducing a number modulo n. And that just means to set it equal to its residue mod n. You replace that integer with its residue. If we have a modulus that's fixed throughout a discussion and we have an integer a, then oftentimes we'll just drop the words modulo n, and we'll just talk about the residue of a. Now we've talked about how divisibility relations give us equivalence relations. Let's generalize that with a single theorem. So the theorem, which is congruence modulo n is an equivalence relation, says that if we have an integer n, where n is bigger than 1, then congruence modulo n is an equivalence relation on the integers. And then the distinct equivalence classes of the relation are these sets. The class of 0, the class of 1, all the way up to the class of n minus 1. And then what's in each class? Well, the class of a is the set of all integers m such that m is equivalent to a mod n. And based on our modular arithmetic theorem, we could say that the class of a can also be written as the set of all integers m such that m is equal to a plus kn for some k in the integers. Okay, let's write the proof, but we're just going to prove part of the theorem. We'll prove the part that says that congruence mod n is an equivalence relation, and we'll leave off the part about equivalence classes. So let's let n be an integer, and n has to be bigger than 1. We'll show that congruence mod n is reflexive, symmetric, and transitive. All right, suppose a is an integer. Since a minus a is 0, and that's divisible by n, then we know that a is congruent to a mod n. That tells us that the relation is reflexive. Now let's let a and b be integers such that a is congruent to b mod n. What we have to do is show that b is congruent to a mod n. Now, since we know that a is congruent to b mod n, then n divides a minus b. And what does the definition of divisibility tell us? It tells us that there is a k in the integers such that a minus b is equal to nk. Well, we can flip that around and make it b minus a is equal to n times negative k, and so that tells us that n divides b minus a. And therefore, b is congruent to a mod n. All right, so that's what we need to be able to prove that this relation is symmetric. And finally, we'll go on to transitive. Let's suppose a, b, and c are integers. A is congruent to b mod n, and b is congruent to c mod n. What we have to show is that a is congruent to c mod n. All right, so knowing that a is congruent to b and b is congruent to c, we can say that n divides a minus b and n divides b minus c. So that tells us that there exist integers j and k such that a minus b is equal to nj and b minus c is equal to nk. Well, if we put these together, we've got a minus c can be written as a minus b plus b minus c, and so that's nj plus nk. We'll factor out the n to get n times j plus k. That proves that n divides a minus c, and therefore a is congruent to c mod n. And that now proves that the relation is transitive. So we've proven it's reflexive, symmetric, and transitive, so that proves it's an equivalence relation. Okay, that's all for now.